Hi everyone, this video is about proof by induction. So in this video we're going to talk about three types of proof by induction. And those are just ordinary induction, and then something called strong induction. And finally, structural induction. So the main idea was introduced a couple of sections ago when we were proving the validity of certain closed form solutions to recurrence relations. So in that video, we talked about a proof by induction. And that method that we used then is applicable in more general settings. So for instance, here are three statements that we can prove by induction, right? So we can prove that the sum of the first n natural numbers is n times n plus 1 over 2. We could prove that the binary tree, or a binary tree of height n, has less than 2 to the n plus 1 nodes. And we could prove that a convex n-gon has n times n minus 3 over 2 diagonals. So all of these questions, so what do these examples have in common? Well, they all pertain to objects that are defined recursively. So induction is a method of proof that is well suited to recursively defined structures. So we begin by talking about what's called plain or ordinary induction. And the starting point of this is we have a collection of statements that are indexed by the natural numbers. And we want to show that every single one of those statements is true. So how shall we do that? Well, just like we did a couple of videos ago, we have a base case where we show that the first statement is true. And then we have an induction step where we show that if k is some number bigger than 1 and statement k minus 1 is true, then that will imply that statement k is true. If we can do those two things, base case and induction step, then we will have shown that statement n is true for all n bigger than or equal to 1. And again, as we discussed in that prior video, the reason why this works boils down to modus ponens. For instance, if you know that statement 1 is true, and you know that the truth of statement 1 implies the truth of statement 2, then those two together tell you that statement 2 is true by modus ponens. Then once you have statement 2 being true, you then can use that together with the fact that statement 2 implies statement 3 to determine by modus ponens that statement 3 is true. So lurking behind this method is this idea of modus ponens. Okay, as our first example, we are going to use induction to prove that the sum of the first n positive integers is equal to n times n plus 1 over 2. So the nth statement here is this statement here where we assert that 1 plus 2 plus 3 up through n is equal to n times n plus 1 over 2. So statement 1 would just be what we get when we replace n by 1. So that's 1 equals 1 times 1 plus 1 over 2. The k minus first statement is where we add 1 plus 2 out through k minus 1, and that's asserting that that sum is equal to k minus 1 times k minus 1 plus 1 over 2. And then here we have statement K. Now, all of those objects are going to be playing a role in our induction proof. Okay, so here's how the proof goes. Right, so first we have the base case where we want to show that the sum of the first positive integer, namely 1, is equal to 1 times 1 plus 1 over 2. And indeed, that's true, right? The sum is equal to 1, and then when we plug in n equals 1 into this formula, we again get 1. So that means that the base case holds. That is, statement 1 is true. Now what we want to do is show that statement k minus 1 implies statement k. That is, if statement k minus 1 is assumed to be true for some k bigger than 1, we're going to show that that implies statement k is true. So statement k minus 1 is this equation, so we're going to assume that that equation holds. And now we want to show that statement k is true. So we begin, to show that statement k is true, we begin with this sum. So we're adding all of the numbers, positive integers out through k. Now that sum includes the sum of all of the positive integers out through k minus 1. Now our induction hypothesis says that this bit right here is equal to k minus 1 times k minus 1 plus 1 over 2. So we're going to take this bit that I have isolated in the curly braces and we're going to replace it with that using our induction hypothesis. And then we still have this k on the end that we can't forget about. So now we have an expression to simplify, and when we simplify it, we see that it does boil down to k times k plus 1 over 2. So the upshot is that we have verified that statement k is true, given that statement k minus 1 is true. So that's the end of the induction proof. We've proved our base case, and we've proved our induction step, and therefore by induction, the sum of the first n positive integers is going to be equal to n times n plus 1 over 2. All right, in our next example of an ordinary induction, we're going to recall the Koch snowflake. Okay, so remember, this is the fractal shape where you begin with an equilateral triangle, and then that's your base case. And then in the recursion, every time, in the previous figure, if you've got a line segment, it's replaced by this tent shape figure. Okay, so line segment is replaced by this new figure which has 4 line segments. So this one line segment is replaced by a shape that has 4 line segments and it looks like a tent, right? So you might recall from the video we had before that if you keep applying this recursive definition, you get this fractal type shape that starts looking a little bit like a snowflake. So anyway, what we're asserting here in this theorem is that the nth figure that we get from this recursive definition has 4 to the n minus 1 times 3 line segments in it. So we're going to prove this theorem by induction. And it's probably good for us to remember what's being asserted by the theorem. So the theorem is asserting that the nth figure in this Koch snowflake has 4 to the n minus 1 times 3 line segments. Okay, so there's a base case and an induction step. So for the base case, we need to show that this statement is true when n equals 1. And indeed it is, right? Because in the first figure, K1, we get an equilateral triangle that has 3 sides. And when n equals 1, 4 to the 1 minus 1 times 3 is equal to 3. So the statement is indeed true when n equals 1. And now we have the induction step. So our hypothesis is for some k bigger than 1, let's suppose or imagine a world where the statement is true for the k minus first figure. That is, the k minus first figure is composed of 4 to the k minus 1 line segments. And then what we want to do is show that that implies that the kth figure is composed of 4 to the k minus 1 times 3 line segments. All right, so, well, how do we do this? If we want to form the kth figure, we take every line segment that was in the k minus first figure and replace it with that tent-shaped object. In other words, each line segment in the k minus first figure is replaced with 4 line segments in the kth figure. So we are taking the number of line segments in the k minus first figure and multiplying by 4 to get the number of line segments in the kth figure. And indeed, if we apply the induction hypothesis, that gives us 4 to the k minus 1 times 3 segments, which is what was required. So in the last video, we talked about the recursive definition of the reverse of a string. And in this example, what we want to do is show that that definition does what we think it will do. That is, if we apply this string reversal procedure that's given up here in this recursive definition to a string A1 through AN, then the result should be just the symbols written in the opposite order. So here we prove the theorem by induction. And again, I want to remind you what is being asserted. So what's being asserted is that if we have a string of length n, and we reverse it, then it's just the string we get by writing the symbols in the opposite order. All right, so we're proving this by induction, and the first thing to do is show the base case, which is what happens when n equals 1. So if n equals 1, then our string consists of a single symbol, and the reversal of that string is the same as the reversal of the empty string concatenated with A. And then remember, our definition says that we bring the A out in front, and then the reversal of the empty string is just the empty string, and then we remove the empty string. And so we get that the reversal of A is just A, which is what we would expect from this formula when n is equal to 1. So it works when n is equal to 1. Now let's suppose that k is bigger than 1, and the reversal function does what we expect it to do for any string of length k minus 1. And then we want to show that that implies that the reversal will work for any string of length k. So we begin with a string of length k, so there it is, string of length k. And we apply the reversal function to it. Now, the reversal function says that you peel off the last symbol, put it out in front, and then take the reversal of the remaining string. Well, our induction hypothesis tells us that the reversal function works as expected for strings of length k minus 1. So I can take this string, the reversal of it, and write it as we would expect. And then we have the a sub k out in front. And what we wind up with is, in total, is what we expect out of the reversal of this string of length k. Okay, in the last video, we talked about line maps. And remember, a line map is a recursive object where you start with a blank rectangle. That's a line map. And then you can form another line map by just simply adding a segment. That's a new line map. And then you get another line map by adding another segment across the rectangle, and so on and so forth. So our theorem here tells us that any line map can be two-colored. So what that means is that we can assign two colors to the regions that are formed by this line map in such a way that any two regions that share a line segment border have different colors. So you can see this is a two-coloring. What's pictured here is a two-coloring of a line map. Right, and the theorem asserts that any line map can be colored in that way. Okay, so here's the induction proof of that theorem. Remember, the theorem says that any line map can be two-colored. So the induction, the statements are based on the number of lines. So our base case happens when we have 0 lines. So if we have 0 lines, remember we just have this blank rectangle, and it can be two-colored trivially just by using a single color. All right, so the base case holds. Now for the induction hypothesis, we're going to assume that if you have any line map with k minus 1 lines, then it can be two-colored. So our goal is, assuming the induction hypothesis, can we show that a line map with k lines can be colored? So let's start with a line map with k lines, say M. It's got k lines. And what we're going to do is we're going to remove one of the lines, this little l. So we're going to remove it from M. That's going to give us a line map with k minus 1 lines. And because we have a line map with k minus 1 lines, our induction hypothesis says that it can be two-colored. So once you've two-colored this line map with k minus 1 lines, you put back the line L that you removed, and you reverse all the colors of all the regions on a single side of L. If you do that, then what you will get is a two-coloring of the original line map M, and that proves the theorem. Okay, now the words on the previous slide might have been insufficient to give you an idea of what was going on in this coloring business. So let's imagine that we have a line map, and let's say it's got 3 lines in it. Okay. So what we want to show is that this thing can be colored. And the idea is to remove one of the lines. So let's do that. So we're going to remove this line right here. And then our induction hypothesis is that the line map that we have that has 1 fewer lines can be two-colored. So let's two-color it. So our two colors are going to be green and white. Now what we're told is to put the line back in. So there it is. And then we're going to reverse all of the colors on one side of the line. So we are going to reverse all of the colors on this side of the line. So below the line, we're going to reverse the colors. So that means all the white will become green and all the green will become white. So this white becomes green. And then this green here and there becomes white. And then what we have is a coloring, a two coloring of the line map with 3 lines. Okay, so how is it that we do inductive type proofs? So the first thing is you need to establish a base case or prove that the property holds for the simplest object. And then you have an induction hypothesis where you suppose that the property holds for an object of some level k minus 1. And then your inductive step is to show that given the induction hypothesis, the property holds at level k. So in the previous examples, we've been dealing with ordinary induction. And now we're going to move on to discuss a method of proof called strong induction. So it's the same sort of idea where we have statements that are indexed by the natural numbers, and I want to show every single one of those statements is true. So our base case is that statement 1 is true. So that's no different from ordinary induction. But now in the induction step, we do something a little bit different. Instead of showing that merely that statement k minus 1 implies statement k, what we're going to do is show that if we know all of the statements that are prior to k are true, then that will imply statement k is true. Right, so again, the difference in the induction step is that instead of just assuming that the immediately prior statement implies the present statement, we're going to try to show that the truth of all of the prior statements imply the truth of the present statement. Okay, one application of strong induction is to give a closed formula for the Fibonacci numbers. Okay, remember the Fibonacci numbers are given by this recursive formula. So f of n is equal to 1 whenever n is 1 or 2. If n is bigger than 2, we get f of n by adding the 2 previous values of f. Okay, now what we're asserting in this theorem is a closed form solution for the Fibonacci recurrence relation. So we're asserting that f of n is this quotient where alpha and beta are these fractions, both involving the root of 5. Okay, before we get on to the induction proof of this fact, remember that, or we're going to observe rather, that, remember alpha is 1 plus the root of 5 over 2. And beta is 1 minus the root of 5 over 2. You can check that alpha and beta are the roots of this quadratic equation. X squared equals x plus 1. So this equation will provide an identity for both alpha and beta. Right? Alpha squared will equal alpha plus 1, and so too beta squared will be equal to beta plus 1. Okay, now we're ready to prove the theorem. Now let's remember what the theorem is asserting. It's saying that the nth Fibonacci number is alpha to the n minus beta to the n over alpha minus beta. Okay, that's what's being asserted by the theorem. Okay, now our base cases are the simplest cases. And now remember, for the Fibonacci numbers, that's n equals 1 and n equals 2. So f of 1 and f of 2, that is the first and second Fibonacci numbers, are both 1, you might recall. Meanwhile, if you plug in n equals 1 into this formula, you get 1. And similarly, this happens when you plug in 2, right? Alpha squared minus beta squared over alpha minus beta. Remember that we have this x squared equals x plus 1. That's going to be true when x is either alpha or beta. So that means that alpha squared can be replaced by alpha plus 1, and beta squared can be replaced by beta plus 1. So f of 2 is this, which is that, which is that, which is that. And so this formula, alpha to the n minus beta to the n over alpha minus beta, does indeed work when n is equal to 1 and when n is equal to 2. Okay, now it's time for the induction step. So our induction hypothesis is as follows. So we imagine a value of k bigger than 2, and we are going to suppose that the ith Fibonacci number is given by this formula, alpha to the I minus beta to the I over alpha minus beta, for every I that's less than k. Not just for I equaling k minus 1, but for every I that's less than k. And then what we want to do is show that the kth Fibonacci number is given once again by this formula. So we use our recurrence relation, right? The kth Fibonacci number is the sum of the previous two. But according to our strong induction hypothesis, the kth minus 1 Fibonacci number is this quotient. The k minus second Fibonacci number is this quotient. And now you need to add all that stuff together and simplify. And when you do it, you wind up with this quotient. But remember, alpha plus 1 can be replaced by alpha squared. Same thing with beta plus 1. It can be replaced by beta squared. And when you do that, after all the dust settles, you wind up with exactly what you wanted, that the kth Fibonacci number is given by this quotient here. Okay, so our next example of strong induction involves a very old theorem. In fact, it's due to Euclid, that says that any number bigger than or equal to 2 is either prime or a product of primes. So this is strong induction on n. So we begin with the simplest case, and that's n equaling 2. So n equaling 2 is prime, so the theorem holds when n equals 2. So our induction hypothesis now is we pick a value k bigger than 2, and we're going to suppose that every single number now less than k is either a prime or the product of primes. So for an induction step, we now look at this number k. If k is prime, then we're finished. If k is not prime, then it can be written as a product of two numbers p and q, where p and q are both bigger than or equal to 2. And then because of the induction hypothesis, both p and q are either primes or products of primes. And so when we put p and q together in a product, because p and q are both either prime or products of primes, k then must then be a product of primes. And that finishes the proof. Okay, our final type of induction proof is called structural induction, and it is particularly useful in verifying properties of sets that are defined recursively. So, for example, Let's imagine a set X contained in the integers where, as a base case, we know that 4 is a member of X. And then we have two recursions. So if little x is in capital X, then x minus 12 will again be a member of capital X. And our second recursion is if x is in capital X, then the square of x will be in X. So for instance, if we want to start listing off a few things in X, certainly 4 will be there. 4 minus 12, which is minus 8, will be in there. The square of 4 will be in there, so 16 will be in there. Minus 8 is in X, so its square is in there, which would be 64. So there are like a ton, infinitely many things that are in this set X. So what we want to do is show that every element of X is divisible by 4. So the way that we do this using structural induction is that we show this property is true in the base case, and then we show that the recursive cases of the definition preserve the truth of the claim. That is, let's suppose we have an X in our set that has the given property. When we apply the recursion to that X, we should get another object that also possesses the desired property. That is, suppose X in our set capital X is divisible by 4, then when we apply either one of these recursions, we should get a new object that is also divisible by 4. Okay, so let's check that. Well, in the base case, we know that 4 is an element of X, and 4 is divisible by 4. So the base case holds. Now our induction hypothesis is, let's suppose we have an object in our set that's divisible by 4. We now need to show that any object we form by recursion will also be divisible by 4. So if x is divisible by 4, meaning x is equal to 4a for some integer a, then x minus 12 is 4a minus 12, which is 4 times a minus 3. And so this new object that we form by R1 in X is also divisible by 4. Likewise, R2 tells us we can form a new element of capital X by squaring little x. Well, x is equal to 4 times a. 4 times a squared is this, which again is divisible by 4. Therefore, the recursions R1 and R2 always produce integers that are divisible by 4, given that the original number that you started with was divisible by 4. And so that's the end of our proof by structural induction.